It's an indication of the complexity, but it's not always accurate. In asymptotic evaluation of complexity, in algorithms or in large circuits, it makes sense to count the levels, and you assume that each level has a delay of 1. And then second solution has a delay of 2, third solution has a delay of 1. This is better. But what's inside the box may be more complicated. And there is an indication in here that is more complicated, because I'm trying to solve a problem which is a two-step problem in one step, then the one step is more complex. Now, somebody asked me in the break about fan in and fan out. Then I will assume you know what repetitio mater studiorum est. Okay? That's English, if you don't know. Mm-hmm. No? Was it English or no? What do you think was that?
Kind of mixer.
Latin, right? And I said that repetition is the mother of study, which is a famous quote. Now, when I have a gate, the delay of that gate, the capability of that gate to transfer a change from input to output will depend on two things, in the top of other things which are technology, whatever. The number of inputs of the gate, which is called fan in, and the number of gates which the gate is driving, which is called fan out. Both of them will contribute. And when I make an analysis at that level of abstraction, I don't see that much about those. I just see that there are more inputs. But this is already a hint that that will be probably more complex. Okay. Now, the question is, how much redundancy do I need in order to play those tricks? If I have no redundancy, forget it. If I have some redundancy, I can play the trick, and the question is how much? Why am I asking myself how much? Because redundancy means extra money. The higher the redundancy, the higher the maximum digit set, the maximum value of digits, then the more bits I will need to represent the digits. You know, in here, when I write a digit, is just one unit. But in hardware, that unit will be represented by a bundle of bits. We don't have technology which can support more than 0 or 1. Or we could also go for -1, 0, 1. That actually, do you know why we do business in Boolean? Why in Boolean like 0, 1 and not in -1, 0, 1?
Smaller hardware?
I don't know, maybe not. We do that.
Because we cannot save 3 states.
I can give you an example of how I can. If I represent values in current, I can have no current, positive current, or negative current on the same wire without having redundancy in wires. What we do is we represent values in voltage, 0 or VDD, then 0 or 1. If I go for current, I can have 0, 1, 2, or -1, 0, 1. I can also do extra things like, this is my voltage domain, and in general, what we do today, here is 0 volts, which is equal with 0 logic, and is this vicinity, whatever it's in the neighborhood of 0, it's 0 logic. Here it's VDD, and whatever is in this vicinity is 1. But I can also split this domain in parts and can say, here I have a 0, here I have a 1, here I have a 2, here I have a 3. Then I have more accuracy, and then I embed more information in one wire. Why do you think we don't really go for that? Yes, people from microelectronics should tell me, not people from embedded systems. No? And you're not from microelectronics.
No.
No.
But I have some.
No, I just want people from microelectronics to tell me. Yes?
Maybe if you
Yes. Then the problem is that I would have some troubles in telling whether it's a 0 or a 1. If I have noise in my circuit, I have to be able to say this is the neighborhood of 0, this is the neighborhood of 1, and this is the no man's land. And if they overlap, I have a problem. And that's the reason why multi-valued logic is not a real option today. From the theoretical point of view, it's a lot better, because I could represent larger digits with one wire. Now, there is an interesting theorem which is saying that the most effective hardware will be obtained if you do logic in radix E. You know E from the natural logarithm? Then we could choose 2 or 3. The choice for 2 was because it's more natural in implementations. And because representing in current, even though robust and simple option, has a problem, which is called energy. What we like systems which are not consuming anything. And the beauty of CMOS is that whenever the circuit is not moving, it's quiet, there is no real consumption. Or at least it used to be like that. Because those new devices, you know, the nanotechnology, what is called leakage, it's getting more and more important. But in this course, we will not talk about those things. We just touch them from time to time because we need them. And the redundancy is very important, and I should diminish the redundancy as much as I can in order to have, you know, cheaper cost for fabrication and less complexity. But I have to add some redundancy because otherwise things are not okay. And I can compute the redundancy. It's a redundancy index, and here it's an example on how can I operate the same kind of trick with a redundancy which index of 2, then instead of having digits between 0 and 9, I have between 0 and 11. This will be enough to give me choices to do good work. Okay. Now let's see what else we have. Okay, this is a more general aspect. We said I can do kind of parallel addition if I go from normal representation into redundant representation, but this redundant representation is not what I really want. Then in order to make use of the beautiful scheme that we discussed last hour at the end, you have to do two things. I have to move from my non-redundant to redundant representation, and this is usually very cheap. It will not require calculations, it's mostly 0. Then I do calculations, but that I have to return into my universe. My numbers in the processor are stored in a non-redundant way. Now, there is a kind of simple rule. If whatever I win here in the middle is not large enough, forget it. Because the cost of coming back from redundant to non-redundant may actually kill that. And there is a corollary to this. Go into a redundant or into another representation whenever you stay there longer. If you just make a conversion, you do a calculation, you convert it back, then your conversion will actually be the dominant factor in the calculation. And whatever you win in doing calculation fast, you lose in conversions. And this is true in many other cases. Now, this is the first utilization of redundancy in computers, and it is related to the representation of sums in a calculation where you have a series of additions. Then when you have a series of addition, in normal, what you do is you make an addition, which means you propagate the carry and you get the result. You started in binary with two numbers, you end up in a binary result. For the next iteration, you have this result, you add another number, you end up again in binary. Then each and every iteration of this summation, it's like I'm computing sum of xi, where xi are, k integers. Instead of doing that, I can go for redundant representation, which means that, to remember, whenever I learn to come here, probably the course will finish. Then I can do this addition and propagate the carry, but I can also do this addition in this way, which is no carry propagation, and temporarily I go from 0, 1 to 0, 2 as digits. Now, when the next number is coming, I will obtain this result. I'm doing parallel addition. There is no interaction between the digits. But when I get the next number, I have a problem because I'm blowing the digit value. I get some digits which now are 3. I am rewriting those based on what we discussed thus far, and then I end up again in 0, 2. And I can continue this addition, and at the last iteration, I will do the conversion from redundant to binary. Which means that now if I have to add k numbers, Gesundheit, or Gesundheit. No, this is said also in English. You will hear that mostly in US. You didn't know that. Americans, they speak a lot of languages. Why don't you trust me? Did I say something wrong? Okay, where was I? Then if I add k numbers without doing the trick, the delay for the calculation will be k times the delay of adding two numbers, which will depend on the number of bits. Then I have k times a function of n, where n is the number of bits. If I play this trick, each iteration will be very short, because will require such a rewriting. And then there is no dependency on the dimension of the numbers. And it's a weight. It will be just a function of k, how many I have. And in the last step, when I'm making the conversion, I will have to do a real addition, and then it will be k plus something which is a function of n. Then I moved something which was a product of k and n into k plus n, which is a big advantage if I think in complexity. And this is based on this trick, on what is called stored carry. Because you don't really transport the carry, you just store it in an extra value. Now, quite sure in order to do that, I need some special hardware. We didn't speak that much about this guy, but this guy is actually our basic brick for arithmetic circuits, full adder. You take 2 bits, a carry in, you generate a sum, you produce a carry out. And this is a full adder which can deal with different kind of things, then assumes inputs in 0, 2. You don't care exactly how this will be designed, but as a concept, you are able to use this. But as you see, I say a digit, and this is in theory one item, and when I represent the digit, I need more bits. And this is one representation. It's not the only one. If I have digits between 0 and 1, I will need 2 bits to represent. And I make a convention. 0, 0 is 0, 0, 1, 1, 0 is 1, 1, 1 is 2. It's a convention. It doesn't have to be like that, it's one of them. There are many others. But as long as we speak the same language, we understand each other. If I use a convention, you use a convention, then we have a problem. Now, that technique, you will see it a lot. This is a technique which helps us to deal with multiple addition and to deal with multiplication in a smart way. And this is the representation of what is called carry save addition, or 3 to 2 reduction, or 3 to 2 compression. I take 3 numbers in binary, and I produce 2 numbers which are the sum of those 3. This is the dot representation. Then I have my previous value of the sum, which is represented as 2 numbers. It's between 0 and 2. Remember the digit. I have the new number, and now what I do is very simple. In each and every column, I apply a full adder. It takes 3 dots and it produces 2 dots. This is the sum, this is the carry. And those full adders are working in parallel. I like parallelism. Serial stuff, not good. Parallel is fantastic. There is another way to do things, and this has also some utilization. It's called 4 to 2 compression. And I take now 2 levels of compression because my basic building block is a full adder. Then I take 4 numbers. These are from the previous result. This is called double stored carry. And I make 1 and 2 compressions, and I obtain the result. Then you see dot notation, it's giving me some insight on some approaches, some things that I can do with numbers. And there is a different way of representing those digits, and I can encode them in different ways, and we'll see that I think a bit later. It's not here. Now we are revisiting a bit, you know, the story with those dots. When I do a multiplication, those are 2 numbers in 2's complement. Remember, those are negative guys. When I make the production, the partial product matrix, what I do is that those are negative. And this negative is adding with those positive and this negative. And this will complicate my thing because what I know is just to add number with the full adder. And I want them to have the same weight. And what you do is you make sign extension. Remember I said I can repeat the sign 1,000,000 times and the value will be preserved. And what I'll do is I'll take this and I'll repeat it until this moment. And this until this moment. This is called sign extension. When I do that, those additions on columns will make sense. This is good, it's robust, it's nice, but it will cost me some hardware. There is another technique which is called bow-willy, where you replace a negative number with a positive number. I'll come to that whenever we'll discuss multiplication. I don't know why Farhani chose to put it here, but what you have to remember for sure from this story is that you have to be careful to add apples with apples and pears with pears. I saw it many times in exams, situation where you are not sign extending and you get a wrong result. Then always when you shift numbers, you will see that is required for multiplication, you have to sign extend. Okay, this is something more about, let's say, set digits conversion. You see this is a serial conversion. When I'm rewriting things, you know, from one to another, this is the conversion at the end. Then I did conversion from non-redundant to redundant. I did my addition, and now I want to return. And you see, return is not simple. There is no way to parallelize it, because return means propagation of carry, means actually doing an addition. You see also here, you have now, this is a more simple one. It's between 0 and 2, and you replace all the digits which are 2 with a carry and 0 in the current position. You can also solve it by an addition. then essentially conversion from non-redundant to redundant is free. Operation on redundant is faster, but it will require more hardware. There is parallelism in it. Conversion back will require an addition. But I started with doing an addition, right? Then if I just do an addition, as I said, what will cost me? It will cost me one addition, which is a normal addition, plus some overhead, which is the parallel addition in redundant. Then I'm not winning anything. If I stay in redundant longer, then I win. Okay, that's another conversion, yet another conversion, and this is a beautiful taxonomy. Okay? You know what a taxonomy is. Okay? It's a classification. And this is telling me about how different redundant signed digit numbers are looking. And what we do is, most of the time we rely on positional radix are non-redundant, and this is what we do. Those do have theoretical value and some application in practice. But it's giving you a view on the field of possibilities. You can even get the feeling that only the sky is the limit. Okay, there are many things. Then this is making your life as designer not very simple. When you design special purpose stuff, essentially, when it's about general purpose solution, it's simple. You go standard. But when you do special purpose, you should try to investigate which of those is the best one. Okay, I was hoping this slide was earlier, but you know, better later than never. This relates to the way I can encode digits which are not bits. And it is about encoding signed digits. Then I have digits which can be, in this case, 0, 1, and minus 1. And this is giving you a feeling about what I can do. I can encode them as signed value. Then the first bit will tell me the sign, negative or positive. The second bit is the value. I can encode them into complement. Then the value of the encoding will give me the number. I can encode them as negative positive. When both negative and positive are 0, I have a 0. And I can also encode it in a decoded way, which means I use no compression, there is no decoding, it's just each situation has a separate bit. Then a digit, a signed digit, can be represented with 2 bits or with 3 bits. Why would I go for the last one? It looks to me a bit silly. Is it? Instead of 2 wires or 2 registers to keep the bit, I will have 3.
Yeah, but if you are doing some process, it will be simpler.
You are getting in some direction. Yes.
You use only one bit at a time to make it 1. I don't know why. I
No.
think
Yeah, this is fully decoded. Then I don't have to make any interpretation of the encoding. And what he said is right in the sense that I will spend more area in my circuit for storage and for wiring. However, the meaning of the digit is straightforward. I know exactly if this digit is 1, 0, or minus 1 from a fully decoded bit. Then there is a price to pay in area, but from the delay point of view, the last decoding is better than the previous for the performance of the hardware. But most of the time we just use to complement. The reason why we use to complement is because for operation on digits, on signed digits, we can use normal addition, which we know from to complement. Then the hardware support is straightforward. Okay, those are other kind of conventions, you know, parameterize them. You you should like it too, because you see there are very beautiful drawings. Now, this is a trade-off. I'm using signed digits and I'm using redundancy in order to make things fast, to kill the propagation of the carry. But this will cost me area. Then what I can do is I can have a hybrid. And the hybrid will be, I have some positions which are bits, and after a group of bits, I have some signed digits. Here I have redundancy. The idea will be now that I can do totally parallel addition on groups, that each group can be processed separately, because there will be, or I have to take care that there is no transfer between the groups. But inside the group, I have carry propagation. Then I am slower, but I'm also cheaper. And again, depending on the application, this can be a good solution. Yet another bullet. Now here it's a theory which is actually summarizing what we discussed on totally parallel addition. That if I have a representation in a certain radix and I have, you know, 2 digits, first I compute the positional sum, then I rewrite that as an intermediate sum and a transfer. I'm actually doing that kind of rewriting. We did that in the previous examples a lot of time, and then I do the final addition. This is the diagram. Now there are some constraints, because I have to choose the dynamic range for the transfer. When I rewrite the position sum, I can generate, being redundant, I have freedom. And I can rewrite the numbers in different ways. However, I have to be sure that whenever I'm generating the transfer, this transfer will not generate a carry further. That this transfer will be absorbed here. And this is only possible when this plus this cannot be larger than beta or smaller than alpha, where beta is the maximum digit value and alpha is the minimum digit value. Then if I do that, I have a totally parallel addition, which is great. We already saw that. The misery is that for binary is not functioning. Then you need to have radix higher than 2 and redundancy higher than equal to 3, or you have to have something like that. If you want to go for radix 2, it's not really working, but is working with one more step. Then it's not, as we saw before, with 2 stages, computing, rewriting, and done. You need an extra step, and this is what you have here. And essentially it can be in 3 steps, and the story is the same. You even get a warning from the calculation, then behind you something is happening and you have to take that into consideration. Or you can do look ahead, then when I'm doing the rewriting, I'm looking to current position and previous position. However, because I don't have enough redundancy, my radix is not large enough, instead of being able to do that in 1 or 2 stages, now I will need 3 stages. In the book, there is no real, there is an example in the book on how you design such a method and how you choose the parameters, the transfer and things like that. It's detailed, but there is a missing diagram there. There are some constants which you have to compute. They are not in the slides, they are not in the book either, but I will put those constants in a PDF file on Blackboard. You will see what I'm talking about when you will start studying. Then basically, when I choose a system, I have to make some calculations to see the dynamic range of my system, then I have to determine the redundancy, and then I have to determine the dynamic range for the transfer in such a way that I'm fulfilling this. which will guarantee me that totally parallel addition can occur. And here it's an example on how this is working with the warning. You see I have more steps now, but it's still parallel and I'm not having transfer of carry. Okay. Now, essentially totally parallel addition is beautiful. It's a nice approach, but in practice it's not always applicable. And there are a couple of reasons for that. When you crunch numbers in a processor, you have branches. And you have to know branch on 0, branch on negative, branch on positive, things like that. Now, when you have a number in binary, in 2's complement notation, you know directly if it's negative or positive, or if it is 0. When you have it in redundant representation, this is getting a bit more complicated, because you cannot really tell how those are, and it's not that simple to compare two numbers. Then I said I go into redundant, and I stay into redundant as long as I can, and then I return. Now that kind of convert and support functions, which are required for a processor, will ask me to come back from redundant to non-redundant. And if I think that in a modern program, in RISC instructions, each and every 5 instructions I have a branch, you see that I will have to return very often from non-redundant. And that's the reason why redundant, it's very good in general, but not very applicable in practice. Okay. And this is another thing which is interesting. You can even get artifacts due to the redundant representation. You see, you may have a transfer digit, like in this case, which is going outside of the domain. Your initial idea will be that I have an overflow. My number is too large. It's larger than my dynamic range. However, this may or may not be true. This is an artifact coming from the way I'm representing numbers and from the fact that I'm not effective in representation in the same way as binary representation is. And this is making things, again, complicated. Then, due to zero sign and overflow, I have to return from redundant to non-redundant very often. If I have programs which are more linear, like digital signal processing, then I'm not returning very often. In a filter, I'm just doing calculations for a long time. I have loops, and maybe from time to time I return. Then this kind of approach is more appropriate for digital signal processing. And it is utilized in digital signal processing. Okay, now we still have some time. I'm behind the schedule, but I'm always behind the schedule. Also because of the technology. Last time it helped us a bit. Hopefully in the future will not help us in that direction, and I'll be able to catch up. This is a different way to look at this problem of coping with carry chains. And this is called residue number systems. And this is coming from an old Chinese philosopher. You heard about Sun Tzu? He wrote a famous book which is called The Art of War. It's still valid. Whatever he's saying there makes sense today. Have you heard about Il Principe by Machiavelli? Okay, Niccolo Machiavelli. Oh my God. He wrote also a book about how to do politics. Then Sun Tzu was a Machiavelli avant la lettre. Then around, I think, 400 something after Christ, he wrote a book about the art of war, which was good for the generals, how to do things, and one of the things which I liked a lot was not to humiliate the enemy, not to put the enemy in a very, very uncomfortable position, because then the reaction will be wild. You don't know what you get. If you want to win, you just do it, you know, slowly but surely. No surprises. Okay, but Sun Tzu also had a very interesting puzzle. He said, I have a number, and I won't tell you the number. However, I tell you the reminders of dividing this number by 3 other numbers. And he said, my number when divided by 7, 5, and 3 is giving me 2, 3, and 2. What is the number? He was not making what we are talking about here, but he was puzzled by that idea. And the idea is now to represent a number in a different way, to make like a signature of the number. Then I use 3 other numbers, which do have to have some properties, and I am claiming that within a certain dynamic range, my numbers processed in this way will give different signatures. Okay? Then instead of writing x, I will write now x equal 2, 3, 2, like this one. This is annoying. Then this is the way I'm writing the number. Now, why will be that interesting? The beauty of that scheme is that now when I'm processing numbers, there is no interaction between what we call those channels. Then if I have another number y here, which is 3, 5, 2, and I add them, I can add in parallel here, here, and here. Then I'm doing the kind of the same story. I'm limiting the propagation of the carry. Then it's the same. I'm starting from binary, I'm moving in the different universe, and there I do things faster. Now those numbers do have to have certain properties. They have to be prime-wise prime. Then 7, 5, and 3 are prime, pairwise prime. If they are not, then I have aliasing. Then 2 numbers will have the same representation. Then, in general, if I choose some moduli, which are in increasing series, and if they are pairwise prime, and then I represent my number not normal, but as a string of those, you know, moduli which I obtain by dividing x by mi, I have a representation of the number. It looks complicated, but there are a lot of advantages in this. And also it's, you know, it's beautiful, it's mathematically elegant, which most likely you don't appreciate, do you? Do you like mathematics? A fair answer will do. Don't have to lie. Don't you? Okay. You don't want to tell me. It's private. Nothing is private to me, big brother. Then, if I want to do arithmetic in residue number system, I have to think about the dynamic range. And let's say my dynamic range is between 0 and 800 or 840. I choose 4 moduli, 8, 7, 5, 3. 8 is not a prime number, but what matters is that they are prime pairwise. Then you will never be able to build something if they are not prime pairwise, because you have aliasing. Then I have this, and then what I do is I represent numbers in this way, and here I have some representations. And I also use the same kind of concept of modulo arithmetic. Then if my x is 21, which in this case is represented by 5010, you know, those are the reminders of dividing this 21 by 8 by 7 by 5 by 3. Minus x will be m minus x in the same way as before, but is distributed over the channels. Then in the channel which is modulo 8, it will be 8 minus 5. Then it's 3. Say 7 minus 0 is 0. 5 minus 1 is 4, and 0. And this is the calculation. I already see that I have independency between the digits. I can process the number in a parallel way. What else do I see? I see that numbers between 0 and 839 do have unique representation. And 840 is similar with 0. Because all the calculation, it's actually modulo capital M, which is the product of the modulo. I can use that budget also in order to deal with sign numbers like you see here between 420 and 419. This depends on what I want. Now there are a couple of things which we need to talk about, but we will not be able to talk about today. But first of all, I want to clarify something. This is still a positional system. Each and every position has a weight, but is not that intuitive because there is no radix. In normal positional systems, I have radix to the power something, and that's the weight of that position. In here, I also have a weight for this position, and for this position, and for this. But that one will depend on how the moduli are chosen, and we'll not talk about that today. But for this system, those are the weights: 105, 120, 300, 280. You see that they are ordered or not ordered, to be fair, because I start here increase and then I'm in the top and here I'm decreasing, which means that I cannot compare two numbers in this system by comparing them from the least significant, let's say, channel towards the most significant channel. If I want to know what is actually this number in this RNS system, this is what I do: 105 times 1, blah, blah, blah. And everything is modulo 840, and this is 9. For humans, it looks bad. Right? You already hate it. I know. But for computers, this might be useful. For the other system which Sun Tzu was thinking about, the weights are 15, 21, and 17. And the number that he was looking for is 23. Or other multiples of 23 within the dynamic range of this one, which is 7 times 5 times 3. Now, today I have to stop. I know you are not happy about that. You would like to stay longer. Then we'll continue the RNS story on Monday. I will publish the first set of homework already, even though probably there are questions on RNS, but you will have the time to go on that. Then you all have Blackboard accounts, right? And are registered for a course. You guys included? You have Blackboard accounts? For Delft? If you don't have, just send me an email or, yeah, we'll solve it somehow. But if you have Blackboard accounts, which will be good to have, then you will see probably in 2-3 hours, you will see the homework on Blackboard.